Hi, everyone. We'll just give it a minute for people to trickle in. And while people join us, I would like to welcome you to the NASEO webinar or workshop today and tomorrow on the future of carbon capture, utilization, and storage, technology and policy considerations. My name is Kirsten Worklas, and I work for the National Association of State Energy Officials, NASEO, and we're really pleased to have a great number of speakers lined up today and tomorrow, as well as have you all attending. Next slide. Before I'll turn it over to David Terry, I just wanted to go over a couple of virtual housekeeping items. I know everybody's pretty familiar with Zoom, but just a reminder that this is a Zoom webinar, so we'll have only the presenters be on video, but we do encourage a lot of questions. You can work on putting the questions in the chat or put the questions in the Q&A box. And we will get them to the speakers. So feel free at any time to put your questions in the chat and in the Q&A box. We can also you can also raise your hand and unmute yourself. If you have any technical issues or questions, please message Shamika Spencer on the chat or email her at sspencer@naseo with any tech concerns. Next slide. Just a quick review of the agenda today. Today, we're going to look primarily at technology considerations for CCUS. Tomorrow, we'll look at the policy side. So we're very pleased to have Dr. Emily Grubert start us off with an opening remarks and keynotes, followed by a panel on where are we now, kind of looking at the technology status of CCUS, and then looking forward, what are some of the technology challenges that we can or have to encounter with CCUS and how to overcome them. And then we're looking specifically at a few CCUS projects and how they've went from the drawing board to implementation. And then we'll have a quick review and preview of tomorrow. Before I hand it over to David, I wanted to thank very much the Office of Fossil Energy and Carbon Management, FECM, at the Department of Energy for supporting this workshop. And with that, I will hand it over to David Terry, Executive Director at NASEO.
Thank you, Kirsten, and thanks for joining everybody today. This has really been an exciting period as interest and work and progress in the area of carbon utilization, carbon capture has continued to evolve and grow. And I want to second my thanks to the Office of Fossil Energy and Carbon Management. The staff there for a number of years has been incredibly supportive of the state energy offices that support both in terms of certainly our work, but the substance of what they do, the contributions by NETL, the contributions by other of the office's staff that we've worked with has been extremely helpful to the energy offices. And I also just want to take a moment to thank a particular person, our director member from Louisiana, Jason Lanclos, who's also on our executive committee, who really brought this issue to the attention of our members, and we began to think about the interest in carbon utilization and carbon capture that a wide range of our 56 state and territory members have, from Louisiana and Wyoming, the Dakotas, and also California, New York, all in different ways and different elements that I think are reflected in this agenda. I think the other progress we're making is seeing where we can find not only the technological innovations, which obviously we need to keep working on, but where are the policy levers. And we've been active with the state energy office's leadership and guidance at the federal level, helping to support supportive policies, whether those are tax or research dollars for the Department of Energy or deployment or other activities across the federal government that support these efforts. So those are all coming together. You'll hear more about that. I think most recently you see that embodied in the infrastructure bill, the bipartisan infrastructure bill, which has some great carbon capture and utilization provisions. We're still working on some of those issues. You'll hear a little bit about that, but I think that's yet another piece that really it allows every region of the country to engage and find the place where where these priorities fit for them. With that, we have some important presenters to move on to, and I don't want to take too much more time, but thank you again to the NASEO staff as well for pulling this together, and our state leads. I'd like to turn it over now and introduce Dr. Emily Grubert, the Deputy Assistant Secretary for Carbon Management at the Office of Fossil Energy and Carbon Management. We're going to hear a keynote speech from her. She has an exceptional background, as you'll hear, really covering a broad range of areas, and I think the holistic sort of ideas that we need to bring to this topic. So I'm going to pause there and turn it over to Dr. Grubert now. Thank you.
Thank you so much, David, and thank you, Kirsten and David, for the kind words. We're always very excited to hear when we're helpful. So really glad to be here, and appreciate you making the time to listen to us talk a little bit about FACM. So to get right into it, my name is Dr. Emily Grubert. I'm the Deputy Assistant Secretary for Carbon Management in DOE's Office of Fossil Energy and Carbon Management, or FACM for short. And I'd really like to thank NASEO for inviting me to this Future of Carbon Capture, Utilization and Storage Technology and Policy Considerations workshop. It's very exciting to see this going forward, and thank you all for making time to talk about these important issues. I come to DOE from a role as an assistant professor of civil and environmental engineering, and by courtesy of public policy at Georgia Tech. So if we've got Georgia people on the line, I'm down in Atlanta actually during our work from home period. In my role at DOE, I oversee the carbon management program, which focuses on minimizing the climate and environmental impacts of fossil energy through technology pathways that include point source carbon capture, carbon dioxide removal, reliable storage, CO2 conversion, and clean hydrogen, which I'll talk a little bit more about over the next 20 minutes or so. As many of you likely know, the Department of Energy is a federal research and development agency. Even though our work is framed by policies established under administration and congressional direction, at our core, we're dedicated to developing energy R&D solutions that benefit all Americans. Government-to-government engagement on R&D pathways is going to be central to the nation's energy successes, particularly during this time of deep transition. And FACM wants to strengthen the feedback loop and hear from you on both existing and emerging energy issues and R&D developments in your respective states. I'm excited to connect with fellow government energy leaders about FACM, CCUS, and broader decarbonization efforts today. In addition to FACM's engagement efforts that are specific to our R&D portfolio, the Department's Office of Intergovernmental and External Affairs is another resource that you should feel free to reach out to. And we've recently established regional specialists to facilitate increased federal to state engagement. I want to start by talking a little bit about some of our R&D as it aligns with administration goals. I know everyone here specifically is excited and committed to dramatically expanding the scope of technologies needed to manage greenhouse gas emissions in order to combat climate change. We're taking this challenge very seriously at DOE, so seriously that you may have noticed that we are now FACM as opposed to the Office of Fossil Energy. So as of July, we have included carbon management in our title and organized a lot of our work really specifically around climate. Our name change reflects the fact that we've refocused our R&D priorities to center our work on climate and carbon management specifically. We're striving to align our R&D efforts to further advance the Biden-Harris administration's mission to cut emissions by 50% by 2030 relative to 2005 levels, produce 100% clean electricity by 2035, and ultimately reach net zero US carbon economy by 2050. I know many of your states and cities have also established executive and statutory goals, and in some cases both, as in California, Oregon, and Maine. This mission and the work needed to achieve it is more urgent than ever, which I know many of you know very deeply. To that end, the DOE's budget request for next year actually includes a 60% increase in federal investment in R&D for carbon capture, storage, conversion, and removal, up to $368 million in 2022. Since 2016, DOE has spent $1.2 billion to develop carbon management approaches. We know these investment numbers will have to move higher for us to truly combat the problem of climate change. The good news is that we're seeing a lot of support from the White House and in Congress for our mission, including provisions in the President's Build Back Better agenda and the bipartisan infrastructure deal that will create clean energy jobs, combat climate change, and support more resilient and healthier communities. As we continue to work with Congress to initiate the R&D initiatives authorized in the Energy Policy Act of 2020, we're also thinking about and planning for new clean energy projects that may be included in the infrastructure bill, including CCS projects. The success of these projects isn't only about getting them off the ground. We must also make sure that they're done in a just and environmentally responsible manner that puts us on a path to net zero greenhouse gas emissions while minimizing and repairing impacts to human health and the environment. Technology solutions will have to be deployed across the economy, from the power sector through the manufacturing sector and beyond. That effort will require an all-of-government approach and involve close collaboration between DOE, EPA, and other agencies, along with industry, and with you as state energy offices and regulators. While we focus on the work needed to scale critical CCUS technologies in particular, we must also incorporate a new way of acting where environmental justice, equity, and workforce development are at the center of our work, particularly as we start to see large demonstrations and deployment of some of these technologies. As we adapt our focus, we will continue to promote job-preserving and job-creating investments in communities burdened by climate change and other historic harms, in addition to those that have worked hard to supply our energy demands. That includes helping those in fossil energy industries translate their skills to new clean energy jobs in their communities. Earlier this year, DOE announced $109.5 million in funding for projects that directly support job creation in coal and power plant communities that are impacted by changes in the energy economy. This is part of President Biden's government-wide initiative to boost the economic potential of those communities. We have a lot of work to do. We in FACM and at the National Energy Technology Laboratory, or NETL, and even the federal government can't do it alone. As with any transformational endeavor, achieving a clean energy economy and net zero carbon emissions by mid-century will require partnerships between government, academia, industry, and others who are committed to reaching those goals. That means we will need your knowledge and expertise, as well as the enormous talent and resources in your respective states as we move in this direction. For our part, FACM's mission centers around investments in technological readiness that helps ensure clean and affordable energy and decarbonization in the industrial sector, while helping facilitate a just and sustainable transition toward a net zero carbon economy. Our work on climate is done with an emphasis on the following priority areas: point source carbon capture, carbon dioxide removal, reliable storage, CO2 conversion, clean hydrogen, methane emissions reduction, and critical mineral production. A lot of what we do is around managing carbon, but our work is more than just carbon. One of our two primary R&D offices, which is called Resource Sustainability, is focused on limiting and cleaning up the environmental impacts of fossil fuel extraction. My office, Carbon Management, is focused specifically on carbon. We investigate technologies to manage the emissions associated with power and industrial sectors, in addition to managing legacy emissions in the atmosphere by coupling carbon capture to the conversion or permanent storage of CO2 to reduce negative climate impacts. We're taking an approach where we are leveraging the learnings and experiences from our demonstrations of first-gen technologies in order to develop the next generation of technologies that will be lower cost, have higher rate of capture, to ultimately develop negative emissions technologies. We intend to look into producing low carbon products from CO2 and optimizing geologic storage of CO2. Our first generation CCUS projects have shown us that CCUS can be successfully deployed at scale and in various industries. And to date, our projects previously have cumulatively captured and injected more than 12 million metric tons of CO2. We know we need to work to increase these numbers. When we think about possible emissions reduction scenarios, aggressive decarbonization is at the forefront. FACM believes that carbon capture, utilization, or storage, which I've been calling CCUS, is necessary to achieve full decarbonization, particularly for industrial sources which have sector-specific R&D challenges. Equally important to our R&D approach is to distinguish very specifically between point source carbon capture that's intended as emissions mitigation, as in the power sector and industrial sector, and carbon dioxide removal technologies that can address legacy emissions that are already in the atmosphere. We also recognize key synergies across these priorities, including proving out durable CO2 storage across our R&D efforts. In the United States, we're fortunate to have a wide variety of low carbon energy options that don't come with the added challenge of managing CO2 or other hazardous air pollutants, and FACM prioritizes using non-fossil approaches where possible. During the decarbonization transition for both power and industry, CCUS is one way to mitigate emissions while carbon-based assets are used for technical reliability and other reasons. But CCUS should not be seen as a blanket solution, and where and how it's deployed takes thought and strategy for it to be successful and sustainable for the long term. The portfolio of solutions to getting to net zero carbon emissions in the US may be quite different than that in other parts of the world. So we do see our role partially as really providing a lot of information and de-risking some of these technologies in a way that may be globally relevant. In FACM, we're increasing our focus on parts of the industrial sector that we rely heavily on, particularly those that are difficult to transition to zero carbon approaches. These include industries like cement and steel production. In fact, earlier this year, FACM released a funding opportunity announcement for $75 million looking into R&D and FEED studies for carbon capture and dedicated storage on natural gas-fired power plants and industrial facilities. Today, our focus on carbon capture is primarily to reduce the cost and increase the capture rate. Some of the advanced technologies that we investigate have moved toward large pilot scale tests and front-end engineering design studies for commercial applications. And additionally, we're leveraging our 20+ years of experience and expertise to apply these learnings to negative emissions technologies, including direct air capture with storage, bioenergy with CCS, and mineralization concepts that can remove CO2 directly from the atmosphere with the intent of addressing both extremely difficult to mitigate emissions and legacy emissions. We're also working on technologies and concepts that take CO2 and convert it into useful products, like building materials such as cement and aggregate, fuels and chemicals, and solid carbon products like carbon nanotubes, which have a wide range of potential applications. Capture doesn't necessarily result in much without storage, and so we have a very robust storage program as well. Our carbon storage program has had various successes over the years through efforts like the regional carbon sequestration partnerships. Today, we're leveraging that work to help optimize and improve storage operations across the United States. We're currently moving forward with the Carbon Storage Assurance Facility Enterprise, also known as Carbon Safe initiative, which aims to develop storage complexes that can store more than 50 million metric tons of CO2. We're currently in phase 3 of this effort, where projects are currently conducting detailed site characterization with the goal of achieving Class 6 underground injection control permits to construct the wells. Infrastructure and field projects like Carbon Safe provide valuable data and information to address key scientific and technical issues that can improve storage operations by validating advanced modeling and simulation capabilities. We're combining this field experience with our lab and simulation R&D to better understand geomechanics in the subsurface. And we're also applying enabling technologies like artificial intelligence to enable real-time decision-making in subsurface operations. When integrated, our capture and storage R&D will provide the necessary technologies and infrastructure to enable deployment of CCUS to achieve our decarbonization goals. Secure and reliable CO2 storage is critical to helping us meet our climate goals. We have a robust R&D portfolio in the carbon storage space specifically to improve storage and operational efficiency, as well as strengthening our understanding of overall cost and de-risking strategies to reduce these costs. These are all particularly critical to enabling and supporting a CCS industry that is safe, economically viable, and environmentally responsible. Building on the regional initiatives and Carbon Safe program that I talked about a moment ago, our goal is to broaden the availability of certified resources for geologic storage through field projects that advance characterization and certification of storage complexes in regions that have known storage capacity, but also in regions where the storage resource potential is more prospective. We're really looking at how we can characterize our ability to store CO2 across the United States. One thing to bring up in the context of this state-oriented audience in particular is that we're very interested in watching some of the Class 6 permitting processes. We know Wyoming and North Dakota already have primacy for issuing these Class 6 permits, and we understand that several other states like Texas, Louisiana, Oklahoma, West Virginia, and Arizona are also considering primacy. We're very interested in working with states in this area. And we're aiming to expand carbon storage demonstrations so that we have more projects distributed across the US and in locations where CO2 injection deep underground is feasible today. In addition to that deep underground storage, we're also working to expand storage to include mineral carbonization of CO2 through alkaline sources from mining. Oftentimes with mining, there may be waste that contains alkaline-rich feedstocks like calcium and magnesium, which can react with CO2 to form a synthetic aggregate that could be used as a feedstock for road building or concrete. In this case, you're remediating two wastes, both CO2 and the waste associated with mining. Let's talk a little bit about our carbon dioxide removal activities. We investigate activities like direct air capture, biomass with carbon removal and storage, enhanced mineralization, improved terrestrial carbon removal and sequestration, like improved forest management, enhanced ocean alkalinity, and coastal blue carbon. So one thing to bring up here is that although we have spent quite a lot of time doing much R&D research on both capture and storage, we're really taking a very diverse approach to thinking about carbon dioxide removal alternatives. Since the terrestrial biosphere and oceans already remove roughly half of anthropogenic emissions each year, CDR requires that these carbon sinks are enhanced beyond today's baseline when it comes to ocean and land-based CDR approaches, which means that we actually do need R&D to understand how this enhancement might happen in a just and sustainable way. Our CDR program is investigating ways to facilitate deployment, build the supply chains for creating negative carbon products associated with CO2 removal, and find new approaches and technologies to remove CO2 from the atmosphere. The key to all of these CDR approaches is validating the economics and markets for these technologies, in addition to having well-defined life cycle analysis of what actually the carbon accounting looks like here. So because the overall goal is to take CO2 out of the atmosphere, we're very, very focused on developing metrics and methodologies for understanding how successful that is being done across all of these different technology spaces. We understand LCA is critical to ensuring and validating that the approaches are truly removing CO2 from the atmosphere, particularly when we have sort of biospheric feedback loops associated. I'd like to talk a little bit about our hydrogen program as well. The FACC Hydrogen program is focused on clean hydrogen production and utilization at the scale needed for utility or large industrial energy users, specifically from generating hydrogen from carbon-based feedstocks with carbon management. So our hydrogen program includes research on clean hydrogen production through gasification of coal wastes, biomass, and non-recyclable plastics, as well as through reforming of natural gas, all with carbon management. Carbon-based hydrogen production that incorporates carbon capture, storage, and utilization is expected by many to play a large role in the decarbonization transition because it's currently lower cost than renewable hydrogen, even with the cost of carbon capture and storage. For industries where hydrogen provides a path to net zero emissions, ensuring that clean hydrogen is available as soon as possible is important. It's absolutely critical, however, for next generation fossil-based hydrogen production to achieve a maximally viable rate of CO2 capture to produce clean hydrogen. Producing hydrogen from biomass with CO2 capture could enable CO2 removal, which is another area of interest in our office. Rapid escalation of carbon capture rates for these carbon-based hydrogens is essential if this resource is to play a role in decarbonization, and this is a big focus of our R&D. Pathway analysis is in progress to identify R&D opportunities to meet production cost and emissions intensity goals. And some of you may have seen the Department of Energy's hydrogen shot announcement, where we're achieving $1 per kilogram by 2030 is the goal. And our pathway analysis includes evaluation of natural gas, biomass, waste coal, and other waste streams as primary feedstocks. We also investigate potential advancements to contemporary commercial technologies like steam methane reformation, autothermal reformation, and gasification, as well as in advanced technologies like chemical looping and pyrolysis. We're also investigating unit siting choices and the potential application of biofuels. Renewable-based clean hydrogen pathways are included as well, and we work very closely with the Energy Efficiency and Renewable Energy Office, which is more focused on electrolytically based hydrogen. Specific enablers for clean hydrogen identified thus far include the reduction of methane emissions from the upstream natural gas supply chain, which is a key area of focus, using renewable feedstocks, and identifying opportunities to site CCUS processes near hydrogen production sites. One of our other programs that is currently underway that is intended to facilitate decarbonization while we're actually making the transition is our long-term energy storage program. The Energy Storage Grand Challenge, or ESGC program at FACM, is focused on advancing a broad suite of low-cost, long-duration grid-scale energy storage technologies and integrating them with fossil-fueled power plants to enable a flexible, reliable, and resilient electricity network during decarbonization. Thermal, mechanical, and chemical energy storage technologies are considered, as these are particularly suited to integration with these existing fossil-fueled assets. Our key focus is on understanding challenges and risks associated with integration of energy storage technologies with fossil-fueled power plants, rather than in achieving incremental improvements to standalone storage technologies. Some of the projects we've funded are focused on developing conceptual design for engineering scale prototypes of fossil integrated energy storage technologies, and also conducting techno-economic analyses. Pilot scale demonstrations are key to actually retiring some of the integration related risks and enabling widespread commercialization and deployment. We planned pre-feed studies and pilot scale demonstrations in FY22 and FY23. That's kind of a summary of a whirlwind tour of the Carbon Management Office. And I want to thank you again for the opportunity to discuss the DOE's CCUS and broader decarbonization efforts from FACM's perspective. As mentioned earlier, please feel free to reach out. We would like to strengthen our government-to-government engagement. And please note that we are available to you if you would be interested in a briefing on any of our R&D portfolios. And with that, I will open it up to questions if we have time, and I really appreciate your time and attention.
Thank you, Dr. Grubert. This was really interesting. I don't see any questions in the chat, but I was hoping if you could maybe talk a little bit specifically about the state energy offices and the NASEO members and how you see their role in supporting some of the things you outlined that FECM is planning under the Biden administration, how we can work together.
Yeah, absolutely. And I think one of the major things to bring up here is that we are really trying to think about our future in terms of really deploying things into the real world and getting them kind of out of the bench, but also in really thinking about this from a place-based perspective. So one thing that we're very, very interested in is really understanding where things can go and why we can actually achieve really appropriate deployment of some of these technologies. And so where we really look to the state energy offices for help with this is in identifying what does your state want and what kinds of things might we be able to help with and facilitate. So very, very interested, as I mentioned, in justice and sustainability. And part of that is really understanding what's appropriate to site where, but we realize there's a lot of infrastructure coming and we want to make sure that we do the best job that we can. So to the extent that we get really very specific feedback and guidance on how we can integrate, we'd really love to hear that.
Great. I do have one question that is asking if your office or FECM in general is collaborating with ARPA-E and OTTT on CO2 use applications.
Yes, so we work a lot with the other offices within DOE and hope to do more of that.
Great. And yes, we've definitely seen some cross coordination across DOE, which is very welcomed. You mentioned the Energy Grant Storage Challenge. You mentioned some hydrogen work. I was wondering if you could elaborate a little bit more on some of these collaborations and where you see kind of that going, especially on the Energy Grant Storage Challenge and the hydrogen work. I don't know if NASEO, together with the Green Hydrogen Initiative, has the Western Green Hydrogen Coalition with some of the state out west. And so there's always certainly very deep interest also on hydrogen. So maybe you can expound on that a little bit.
Yeah, and I think a lot of what guides our integration with the other offices is really this kind of laser focus on net zero by 2050. And we recognize that a lot of our technologies are facilitating for that. And so we work a lot with the other offices to think about where we can coordinate. I think with hydrogen in particular, we've been working across offices really, really deeply, just because we kind of handle the carbon-based hydrogen that includes carbon management. But of course, ERE is focused on some of the electrolytic hydrogen. Our Office of Nuclear Energy is also looking into approaches that might actually integrate nuclear, either electrolytically or thermochemically. And so we think a lot about how our facilities and how our contribution to some of the increasing deployment of this infrastructure might actually play in a way that is really relevant in 2050. And so I think a lot of what drives the way that we collaborate is trying to understand how all of these things are going to fit together in the future energy system. But yeah, certainly very engaged with that. I think we're also engaged pretty heavily in the interagency working group that looks a lot at the way that coal communities and power plant communities are experiencing this transition. So we've been working not just with other DOE offices, but also sort of whole of government agencies with that to try to understand where we fit. A lot of this is still relatively early days, and I expect that we're going to see a lot more of it soon. So if you have suggestions and if individual state agencies have concerns or questions or ideas, we'd really love to hear that.
I need to unmute myself. Thank you so much. I really appreciate it, Dr. Grubert. Again, thank you so much to you and your office for the support of NASEO and this workshop. And going forward, I think you outlined a few very key areas where we're hoping to collaborate with you and your office and FECM in general. And so looking forward to that. And I appreciate you spending time this morning with us, or this afternoon.
Thank you so much for having me. And yeah, if you don't know where to find us, I'm sure we can figure out a way to get in touch, but please do reach out and we'd be happy to provide briefings. So thank you very much.
Great, appreciate it. Thank you. And with that, I would just like to invite Dr. Richard Esposito to turn on his camera. We're going to go right into the next kind of panel. And I'm really excited to have him give us a little bit of kind of where are we now? What is the technological status of CCUS? I think there's a lot of discussion, kind of what is viable, what is financially and economically and technological viable. And we're really excited to have him join us for that conversation. I also wanted to mention that for some that might not be as familiar with CCUS, my colleague Rodney Sobin did an excellent report, which I'm going to put in the chat, on CCUS and some of the overview of the technologies technologies, as well as some policy considerations, which I think lays out very nicely kind of not just the technology, but also what can state energy offices think about as they're grappling with CCUS and how that plays a role in their state energy plans and portfolios. And with that, I'm going to introduce Dr. Esposito. He is the works for the Southern Companies program. He's the Southern Companies program manager of geoscience at the Carbon Management in the Research and Development Group, and he has over 28 years of experience in the electric utility industry. And he received his BS degree and MS degree in geology from Auburn University. And I'm really excited to give you the floor, and hopefully people can put their questions into the chat. I definitely have a lot of questions myself, but looking forward to hearing your talk first, Dr. Esposito.
Hey, Kristen, I'm trying to share my screen and it says someone else's. I can't share it while other participant is sharing.
I think we have your slides lined up, Kelsey. If you just want to say next, then we can just advance the slides if that works for you.
Okay, that'll work. Okay, well, great. Thanks a lot. I appreciate it. I want to thank NASEO for the invitation, first of all, and I also appreciate going after Emily. It really reminds me of how important the Department of Energy is to a clean energy future in the United States, and we're lucky to have an organization like the Department of Energy that's helping us with focus and helping us with these programs. So I really appreciate that. Move the next slide. So I work for Southern Company. We're a large electric utility. We have both a regulated and unregulated business units, but our regulated business units are in the Southeast and Alabama, Georgia, and Mississippi. And so we're pretty diverse on our portfolio of generation right now. We've got coal, we've got natural gas, we've actually got a lot of nuclear. We're building new nuclear. And we've got some renewables in our unregulated entities around the country. And we're, we obviously are looking to decarbonize that fleet. Next slide. We have greenhouse gas goals established, like most electrical utilities. We have net zero established for 2050, 50% reduction goals by 2030, which we've already actually met. But I will have to be honest and say we haven't really met that with a lot of technology. It's mostly been as a result of fuel switching from coal to natural gas. As we shut down coal plants and repower with natural gas, that's 65% less CO2 emissions. So we're really making some huge strides right now with fuel switching. But we do recognize that at some point that we will have to start deploying technology on our fossil assets, and that's where CCS will come into play. Next slide. So look, few beliefs about the future. We do believe that CCUS is critical to our future, and we have to make it affordable to our customers. And also the interesting thing about CCS is it does blend well with other technologies like hydrogen. Emily talked about hydrogen and bioenergy CCS. So the infrastructure, the storage, superstructure, infrastructure for transportation, all blends very well with that. So CCS is kind of works across the board. But we do recognize that it will be a very diverse portfolio of negative carbon emissions for us to meet those 2050 goals. We're very bullish on Class 6 UIC, nothing against enhanced oil recovery. We've just seen some issues with the NRG Parish Station facility with the price of oil and up at Boundary Dam. So we really are very, very interested in Class 6 UIC permitting. And then again, the widespread deployment of CCS, it's going to take continued R&D investment, and that's why we're glad that we have our partners with the Department of Energy. It's going to take a lot of infrastructure. I think, we've got the infrastructure bill sitting in DC right now, trying to figure out what's going to happen with that. But I think that's going to be very important. But it's also it's a three-leg stool of policy, technology, and permitting that'll all play a critical role in the technology moving forward. Next slide. So there's been some commercial deployment to date, and people kind of look at that. But really, there's been a historical lack of drivers in this space, carbon pricing and the timing and the amount of incentives, and of course, policy clarity for CCS to be deployed commercially widespread across the system. there's been a lot of incentives, tax incentives for renewables, which have been around for a long time. And so those have really helped, renewables move forward. And now we've got the tax credits, the 45Q tax credits, which are very compelling. And we love those. And we think we understand how to comply with those and how to get those credits. But even with those credits, we've done a lot of detailed modeling of the credit, looking at the cost of carbon capture. And, none of the credits, even for EOR or for saline reservoir storage, will go the full way of offsetting the costs of a carbon capture project in the electric utility sector, at least. And then there's 48A, which is an ITC, but it's kind of problematic with the heat rate. And so it's not really applicable these days. But we all just got to keep in mind that CCS has very significant direct and indirect financial implications. It's very high capital cost to build this equipment. You got ongoing O&M costs, parasitic load. So you're taking 15 to 20% of the power at the power station to run all the carbon capture equipment. And then you've got, you got to keep your eye on the ball of the transportation and the storage costs being a small percentage, but nonetheless, they are a cost. And then as a regulated utility, we have to look towards our regulators with cost recovery. And then there's, of course, permitting challenges and financial assurance. Next slide. So if you look at carbon capture technology challenges right now, so obviously, if you're down in the range of purity of CO2 from a process or a power plant, you've got ammonia, natural gas, ethanol, which is relatively pure CO2 coming out. Most of what's going on there is you've got some dehydration, some compression, you got to transport it, you got to store it. And so those processes, when it comes to carbon capture, it's a little more straightforward. When you get into cement and steel, which is kind of that middle of the road kind of CO2 concentrations and the emissions, you start having some more difficulties. But when you get into the coal and gas, and especially with direct air capture, you're dealing with a lot smaller purities of CO2 in the flue gas or in the emissions. And so that's when the big costs start coming in, and then you have issues. In the industrial sector, there's heat integration issues. You got multiple sources, like up at a petroleum refinery, you might have quite a bit of CO2 coming off, but it might be a bunch of multiple sources of different purities that you might have to deal with. And then in the power generation, you have load following and dispatch issues with ramping up and down in the carbon capture equipment. And then of course, with natural gas, you've got the increased oxidation, degradation with natural gas, as well as the higher O2 percentages, and then the lower concentration of CO2 in the flue gas for natural gas. And so the 45Q tax credit works very well for ammonia, natural gas, ethanol. Maybe, cement could make it work, but right now in the power sector, that tax credit is not quite there to where it really can cover the costs of CCS. Next slide. So DOE has set a goal, which I think is achievable, of around $30 a ton for capture. And you can see that over time, this cost has come down a lot. I mean, things have gotten even more and more exciting over time with the hopes that we can get this down, the capture costs, especially at coal and gas-fired power plants, to a point where it's comparable to other technologies. Because keep in mind, in the electrical utility industry, I mean, we could choose to build nuclear, we could choose to do all renewables with energy storage, we could choose to do green hydrogen or blue hydrogen, and we could avoid CCS. But if we can get the costs down low enough, then it really makes it a very viable option moving forward. And I think one of the biggest importance here is this FOAC to NOAC to NOAC, the first of a kind, the next of a kind, the next of a kind. So beyond getting different technologies moving forward in this queue of technologies for diversity of technologies available, it's also moving them into the pilot, and then moving them into the demonstration phase, and then next generation demonstration phase. So for example, Boundary Dam, when they did that project, they're saying that if they were to do this project at Shand, which is their other power plant up in Saskatchewan, that they might realize 30 to 40% cost reductions, which is just really staggering, and that's amazing. And then Petronova is the same way with MHIA and their KS1 solvents. They're saying that it's possible that they could reduce the costs of a next of a kind plant 20%. But you really have to do it to recognize that that is really the case. So, it's important that these projects are moving forward and we're getting some FOAC to NOAC to really understand the capital costs and to reduce the O&M costs of these technologies. Next slide. So this is something that I had myself and some colleagues put together with information from GCCSI, and it's sort of the TRL levels of carbon capture technologies. And really, for commercial deployment right now on a large scale, you might be able to do membranes or sorbents on a smaller scale type of industrial application. But for like an electrical utility with a coal or a gas plant, it's really pretty much amines right now in physical solvents. So we're really looking to move a lot of these technologies that are on the left side of this chart to the right and move them up in their TRL levels and try to find some of these transformational technologies, things that are going to get us definitely down to $30 a ton or maybe even lower. And then, of course, I want to point out that you've got a category called new generation processes, which is the alum cycle, which is really exciting, that carbon capture is a little bit inherent to the process of combusting natural gas in that project. Next slide, please. So, and also the value chain needs maturity. So we're, for large volumes of CO2, we're down there in that CO2 storage, dedicated geological storage, enhanced oil recovery. But Emily pointed out a lot of opportunities in the utilization part up there. And some of those are mature kind of processes that have already been going on, but some of them are not. And so those things need to mature. And that's, I think, probably the essence of a lot of the utilization program that the Department of Energy has now and that a lot of industries are looking at. Next slide. So I'd be remiss if I didn't talk about the National Carbon Capture Center a little bit. That's where my office is. This is a cooperative agreement with the Department of Energy for developing carbon capture technologies, kind of screening them out at an early phase and helping to scale them up. There's a lot of partners that are shown on the right part of this slide. But the most important thing about this facility is that, for the most part, there's very little to no cost to the technology vendors who get accepted to come in there and operate and test their technologies. The Department of Energy is funding this, and then there's an industry cost share, and it's sort of this opportunity for people to come and to have their technologies kind of screened by an independent, agnostic, third party who's looking at these technologies with a very open mind. I mean, just because Southern Company kind of operates this facility, we're not picking winning horses. All we're doing is, helping technologies move, because any technology that moves forward that helps the industry as a whole is going to help us. Next slide. And so we've had lots of, hours of operations, lots of technologies tested. We've got an expert staff of capture engineers there, probably the largest grouping of people who know the most about carbon capture in the world that are at this facility. And also very exciting, we just recently built a natural gas boiler. So we're actually testing carbon capture technologies on natural gas with real natural gas, flue gas, instead of just diluting the flue gas that we were getting from the coal plant that was right next door. So we're running it under real conditions, which is very important, especially given the transition from coal to gas in the United States. We need to really be prepared to capture CO2 on natural gas. And then also we're doing utilization studies there, which are really exciting. And also we're doing some studies now with direct air capture. So this is a full service facility, again, funded by the Department of Energy. Next slide. So what's our goals there? What are we trying to do? We're obviously trying to reduce CapEx and OpEx. We're trying to reduce technology risks for carbon capture, mostly on natural gas right now. I think we've done a lot on coal already. We're helping develop detailed engineering designs for the integration of these technologies into existing facilities. And then we're also demonstrating and identifying transformational capture technologies, these kind of up and coming technologies that haven't gotten a lot of attention in the past, like sorbents and membranes and zeolites and things like that, because a lot of people have really just focused on commercial deployment of the amines. Next slide. And of course, we've got absorption that we're looking at, adsorption, membranes, cryogenics is another very promising technology. And fundamentally, a lot of these technologies are very consistent both on coal and natural gas. Next slide. So if you look at this, everything we've done to date, cooperatively with the Department of Energy or individually or the industry as a whole, everything we've done on coal is not, for naught if we shut down all the coal plants or if we start saying, okay, we need to capture on natural gas. There's a lot of very common issues. And I won't go through all these, but you can see this slide and the slides will be available. There's a lot of common issues between capturing CO2 on coal, flue gas, as opposed to natural gas. But there are a few uniquenesses of natural gas. The higher CO2, the lower CO2 concentration is the big deal, higher oxygen content and higher flue gas temperatures. So, understanding those intricacies on deploying the existing technologies like amines and other things that are coming down the queue on natural gas is very important. Next slide. And so the Department of Energy, again, I know I keep mentioning them, but they've got some great programs now. They've offered up, some funding for FEED studies. And so Southern Company does have an award, and we're doing an effort where we're looking at a FEED study on capturing CO2 on natural gas. And this is really important because what this is doing is this is taking, technologies and basically evaluating what the cost would be for the capital cost. We're not doing O&M costs on this study, but looking at the capital cost of what it would cost to build carbon capture technology at this, generation asset that we have in Mississippi, where we're doing this FEED study. And so this really informs our stakeholder for our RFP process and other processes on understanding, the costs of carbon capture, especially in this case with natural gas. Next slide. Infrastructure. So we can't, the technology of building pipelines is there. Our good friends at Occidental Petroleum and Denbury would definitely agree with that. It's just the scale and the magnitude, and also where do we build these pipelines and how big will they be? And understanding source sink matching, is really important. And then thinking into the future about the hydrogen, the 111, that Emily mentioned. Talking about where would we build these pipelines? How is it going to further develop a network of CCS, both for as industry as a whole, but for other industries that might decide to decarbonize later on. Next slide. And I know you guys are going to be talking about this a lot, so I'm not going to go into this, but there are pipeline issues with cost, property rights, and permitting, and there are some things in DC right now that are looking to try and streamline that. But the key thing here that I think everyone needs to realize is that you start getting CO2 pipelines that are more than about 150 miles source sink matching related to storing CO2, you're getting into costs that are going to be paralleling some carbon capture costs for maybe like a 700 megawatt gas-fired power plant. And so that's tough on the shoulders of CCS to be paying the capital costs of building a carbon capture plant, these large, long CO2 pipelines. And then again, the storage cost is probably pretty small compared to that, but it's a big deal. Next slide. So Southern Company, I'm just really proud to announce that we've done so much site characterization. So if you look at the slide on the left, we've drilled close to 20 wells across our system. We've injected CO2. We've built small pilot carbon capture plants. We've pulled together a Class 5 UIC permit back when Class 5 was available. Now we're working on a Class 6 permit in our Carbon Safe project. So we are surrounding ourselves with these issues, and we're really dwelling into this, and especially the issue of source sink matching. Next slide. And so on the storage side, I just really feel very confident about the storage technology. Understanding geomechanics and induced seismicity is still something I think we need to grapple with a little bit. I think we can always improve advanced reservoir modeling techniques. I think there's room for that. Monitoring, we have all the tools we need now to monitor CO2 in the ground. I would love to see some silver bullets come forward. That is something that really just kind of crosses the T and dots the I on that. And then pressure maintenance and remediation, you know, how do you manage sites that maybe you're getting some pressure buildup? And I think those are some of the technical issues that are still outstanding. But the whole process of just injecting CO2 into the ground and storing it long term, I think we're pretty much there on that. But early site certification is real important. It's been real important to Southern Company. These are a couple pictures of some of the sites where we've been drilling at in our carbon safe program. We've drilled 6 wells through phase 2 and phase 3. But understanding whether we would do one-off source sink matching and what kind of infrastructure is needed for that, or whether we'd be doing trunk pipelines and pulling multiple sources, those are the sort of things that we really need to be thinking about. And then all the externalities, which I know you guys are going to be talking about over the next couple of days, about Class 6 permitting and primacy, access to pore space, and whether amalgamation is the thing to go there, and then, you know, securing the 45Q tax credit, and then outreach and public acceptance, and now environmental justice is a big thing that we're definitely looking at. Next slide, and I'm almost done here. So even as much source sink, you know, I'd be remiss as a geologist not to put a fancy map up on the screen, but even as you know, all the wells that we've drilled in the Southeast and all the oil and gas wells that are in the Southeast, we still find ourselves in a situation to where we understand, you know, a certain amount of our service territory where we could pretty positively do carbon storage. And then there's these areas where it would be impossible. That improbable is igneous and metamorphic rocks of the Piedmont, where, you know, there's igneous and metamorphic rocks at the surface and at depth, and you just can't do it there. So any power plants that we would have there, we'd have to pipeline it north or south to areas. And then we're infill drilling and actually doing drilling on our own dime at Southern Company, looking at, you know, these areas where it's possible to do storage, but there's not a lot of information in South Georgia or in North Central Alabama. Next slide. And last slide, you know, I don't have 2021, but the budgets have been really good. And I was excited to hear Emily say that the budgets next year are going to be even bigger. We'll hold her to that. But I think we're, you know, I think all in all, things are going well with DOE and their funding levels. You know, we always want more funding, and we hope that phase 4 carbon safe comes through, and there's lots of opportunities that. And with that, I am done. I think that's my last slide.
Great,
Yeah.
Thank you so much. This was a really great overview, and really appreciate kind of walking through the technology and where we're at right now. We do have a few questions in the chat, so I'll get to them. One of them was sort of, you mentioned kind of the transportation pipeline issue that, you know, if I think your cost that you had on one of the slides might have just represented kind of capture. So how much more would transportation and sequestration mean in terms of cost? And then how does scale affect costs? And would you say that the economics suggest maybe aggregating multiple CO2 sources?
Yeah, there's obviously a benefit on economy of scale and building pipelines. So you can ask, I'm not a pipeline expert, but if you ask, you know, our good friends Occidental Petroleum and Denbury, they would say, you know, the major cost is the land and building the pipeline. The diameter is an additional cost, but it's not a significant additional cost. So, you know, if you're, you know, so a strategic vision is so important here, and that's so difficult in the electrical utility industry. It's like, so what plants are going to be operating 5, 10, 15, 20, 25 years from now? Is that coal plant going to be shut down? Is that older natural gas plant going to be shut down? So a strategic vision in generation planning and understanding what assets are going to be running and when we need to decarbonize those assets, you know, to reach our goals is so difficult. And we go through all these scenarios. And so I would say that, you know, regional, I'm real positive on regional storage hubs and pooling CO2 together from multiple sources, but you just have to be very guardedly optimistic that when you plan that all out and you spend the money for those pipelines, that those sources are really sources in the future, right?
Yeah, certainly. And that certainly points also towards kind of the engagement of the state energy offices and some of the other state agencies that work with the utilities on some of these plans, integrated resource planning, but, you know, working on how that energy policy and energy landscape in the states look. So I'm certain there are points of engagement there. We also had another question in the chat. Given the challenges and lack of takeaway capacity, do you think that the midstream companies will control the carbon capture market?
I don't know if they'll control the carbon capture markets, but I definitely see a lot of service providers, midstream service providers, and people downstream service providers that are stepping up that want to manage CO2. I think we would always own and operate the carbon capture units at our power plants, because those are regulated assets and we want to have 100% control of that. We want to manage that construction. We want to manage that operation. We want to manage that process. Now, we would definitely probably consider Southern Company of, over the gate off tape, pay, and pay a fee for someone to take CO2 and transport it. We're not in the business of building CO2 pipelines, although we have built some. And we're definitely not in the business of managing storage operations, although I think we have a big engineering organization, we could do it. But I think that those would probably be services that we would outsource to, especially in a regional storage hub. Maybe get someone to come into the Southeast, develop a regional storage hub. Maybe we helped get that regional storage hub going through a carbon safe or a regional carbon sequestration partnership project, provide all that information and someone else own and operate it.
Yeah, it's really interesting. Another question that came into the chat was, do you see the combination of above ground and below ground pipelines in the future? I know you're not a pipeline expert, but I'm still going to ask that.
Everybody that I talk to about above ground pipelines just say that's a really bad idea. And I don't, I would like to learn more from the audience if there's someone who can educate me on what the disadvantage. I wonder whether it has to do with just a safety thing, whether you have to have them below ground, or whether it would be temperature variations would impact the phase changes of the CO2 in the pipeline. It might be an issue with keeping the pressure temperature as a dense phase moving in the pipeline. You might need more compression stations, which might be very expensive on above ground pipelines, but that is definitely not my wheelhouse.
I appreciate you expounding on it nonetheless. And maybe I think we're kind of wrapping up, but one final question maybe is sort of, you've kind of outlined some of the challenges, some of the policy challenges too, and where kind of maybe some of the policy shortfalls are. But I was wondering, I know you're focused on the technology, but if you'd look at like state and federal policy considerations and what you from a technological perspective maybe need to move forward, if you have any suggestions for the audience, state energy offices, or even the federal landscape.
Yeah, I get in trouble with my DC folks when I start talking about policy, but policy and technology, go hand in hand. So what I would say about that is, sometimes as a technology guy, it's kind of like, tell us what we need to do. We'll go out and do it. We'll provide the technology to do it. And then, that's where my part of it ends, right? But, it's with respect to CCS, I think there's definitely CCS in our carbon constrained future at Southern Company. I just don't know when and how much and on what kind of assets right now. I mean, the landscape is changing so quickly right now. And, if you told me, for 2050, we might not have to deploy CCS until 2035 or 2040, something like that, to get to those goals. But if you told me that we had to reach our greenhouse gas reduction goals by 2040 or 2035, CCS is going to be more, and it's going to be deployed sooner, and that's why I think it's good for the flexibility of the tax credit. That's one big policy thing. That commence construction date needs to be extended, because for most electrical utilities, we're regulated ones. We're not going to be able to get anything moving forward, for good reasons by 2026, January 1st. That's a non-starter. I mean, that needs to be pushed out.
Great. Well, I don't see any other messages in the chat, and we're just about at 2 p.m. Eastern. So I really appreciate this. This was great. Thank you so much for giving us that broad overview. And I would now like to turn it over to the moderator of the next panel, which will look at CCUS and kind of the technological challenges going forward. And this panel is moderated by Eddie Trevino. He's the director of the State Energy Conservation Office and the Texas Controller of Public Accounts, and he's also a member of the NASEO Innovation Advisory Group. So Eddie, over to you.
Thank you. Thank you, Kristen. It's a privilege to participate on this panel today. As Kristen said, I am the director of the State Energy Office in Texas, and am participating in the Innovation Advisory Group. Today, what we are going to examine in this session is and are the technological challenges and the way forward for carbon capture, utilization, and storage. And so our panel will provide insights into the remaining technological challenges and also provide potential solutions to mainstream CCUS. So we have three panelists, as you can see on your screen. We have Mahmoud Abunaga, a senior fellow for the Center of Climate and Energy Solutions, Aaron Burns, the executive director of Carbon 180, and Amishi Kumar, a program manager for carbon utilization research and development at the Office of Fossil Energy and Carbon Management with the Department of Energy. So we are going to go in the order that you're looking at on your screen right now. Mahmoud, it is time for you to take it away.
Thank you so much, Eddie. Good afternoon, everyone. I am Mahmoud Abunaga. I'm a Solutions Fellow at the Center for Climate and Energy Solutions. I'm glad to be here with you today to discuss some of the challenges and opportunities for large-scale deployment of carbon capture, utilization, and storage. Next slide, please. For those who are not familiar with our organization, CCUS is an independent, non-profit, non-partisan organization that brings together diverse interests to find effective and innovative solutions for climate and energy challenges. We work with both local and global policymakers, business leaders, and other stakeholders to reduce greenhouse gas emissions, promote clean energy, and strengthen the climate resilience of local communities. We are also a participant and co-founder of the Carbon Capture Coalition. It's a broad coalition that brings together energy and industrial technology companies, labor unions, energy and environmental policy organizations. And the main objective is to accelerate commercial deployment of carbon capture technologies. The coalition was launched in 2011 and has built bipartisan support at the state and the federal level since then for different policies, including for sure the 45Q tax credit and almost any other CCUS related policy that happened since then we were involved in. And the main objective is, as I said, is like just to accelerate CCUS and boost the US energy infrastructure development. Next slide, please. I would just like to start with like a brief overview of the current status of CCUS technology before we get into the challenges ahead. It's really important to understand that the core technology we're talking about here is mature. Like it's not like you read in the news or sometimes in certain coverage of CCUS that like a nascent technology, like a prototype. No, the CO2 capture has been performed successfully in industrial facilities for decades. And geologic storage of CO2 has also been around for over 50 years. So it's not that nascent technology that we hear about in certain reports. There are currently at least 26 commercial scale carbon capture projects operating around the world, with 20 more in early development and around 13 advanced development stage, reaching what we call the FEED, like front-end engineering design stage. And it's important to know that almost half of these projects are actually in the United States. So that's something that we need to pay attention to going forward. How the US actually is the flagship for the rest of the world when it comes to CCUS. Large scale carbon capture has been demonstrated and in commercial operation in different existing facilities, including coal gasification, ethanol production, fertilizer production, natural gas processing, and refinery. And it can also apply to new facilities that includes low carbon hydrogen, low carbon biofuels, CO2 removal technology that we will discuss later as well. It's also important to note that the current setting for CCUS emitting facilities, or what we call point sources, are not necessarily co-located with the storage basins that have suitable storage and injection rate capacities. And this would make the cost for the project actually increase if it remains the same way in the future. So that's something we will discuss more in details in coming slides. Here, the United States has actually abundance of geologic storage potential, and that is more sufficient to store hundreds of years worth of carbon emissions And it's also important to note that there are some established markets for utilization, enhanced oil recovery, for example, but there are also growing markets, whether it's cement, aggregates, low carbon fuels, synthetic fuels. Now that we have seen all these facts on the ground, despite all of that, the current carbon capture capacity is less than 1% of the capacity needed by 2050 to meet the climate targets. And these are the IEA numbers. Next slide, please. When we talk about challenges, I would like to separate the challenge into three main parts: capture, transport, and storage. For the capture side, while there is room for improvement in terms of increasing the efficiency of the capture process and using advanced material, these are considered relatively minor barriers. So I wouldn't call them a barrier for larger scale deployment, since the existing technologies already managed to achieve capture rates between 90 to 95%, which is more than enough for the moment. And just to give an example, it's technically now feasible to achieve capture rates beyond or above 95% with only minor, less than 3% efficiency penalty and financial penalty, compared to the compared to a 90% capture facility. Even capture rates above 99% are also possible. But is it worth it to go that far to and sacrifice energy and efficiency penalty? That's something we need to develop through R&D and stuff in the future, but that's not the main barrier for the moment. We can go forward with that. Transport and storage are actually more critical factors that are considered barriers for larger scale deployment. As I mentioned, while there is abundance for geological storage, there is, here in the US, there is mainly one large scale storage project dedicated to permanent, saline permanent storage, which is the Illinois Industrial Carbon Capture project. So that's a big question mark. Part of that is related to permitting hurdles, commercial readiness of storage sites, and we will discuss that more also. In terms of transport, there are currently around 5,000 miles of CO2 pipelines, but these existing pipelines need to be first expanded, and also they need to be optimized in order to connect more facilities to different storage sites in a way that allow them to share these kind of common networks. We have seen recently that also public perception of pipelines projects has made it harder for investors to pursue these kind of projects. And that's an important part of the argument here, is that how to convey the message to the public that not all pipelines are the same. Actually, if we are talking about a CO2 pipeline, that's something really important, critical for the environment. And I'm sure in the previous presentation with Dr. Esposito, he talked about how the safety concern with carbon pipelines are much less than what the public think they are. Actually, it's way safer than we expected. Next slide, please. Since industrial and power facilities tend to be concentrated in the same regions, these industrial hubs offer an opportunity for commercial synergies and economies of scale. And that's why investing in larger scale trunk pipelines can substantially reduce the overall cost by transporting large volumes of carbon dioxide from different emitting facilities to designated geological storage sites. For example, here, if you look at the map here, ethanol facilities that are concentrated in the upper Midwest can aggregate their carbon dioxide supplies and use these shared pipelines to deliver it to geological storage, whether in the lower Midwest or in the Gulf Coast region. And the same goes for other hubs that you can see here. This map here actually was developed by researchers from the Great Plains Institute. They looked into the most feasible near and medium-term opportunities for deployment of regional CCUS projects. These projects can actually unlock massive economic potential for the industrial and the power sector to capture the carbon and safely store it. this research project estimated that more than 350 million tons of carbon dioxide can potentially be captured and stored each year by scaling and optimizing this regional infrastructure. This number, the 350 million tons, is actually more than a 15-fold increase in the current carbon capture rate that we have in the United States. So that gives you an idea how this kind of optimization can be a game changer for CCUS. Next slide, please. These shared networks we are talking about takes us to what is known as like the hubs and cluster model. The concept basically separate capture from transport and storage infrastructure, and this allows some kind of like risk sharing among different like public and private organizations. And we have seen example of this model. Actually, one of the projects that follows that model is like in the center here. The map here is the H2H Sultan project in the UK. It supports carbon capture deployment by co-locating hydrogen production and industrial centers that will use the end product, which is like the captured carbon and industrial heat in this case, creating basically new markets and helping hard to decarbonize industries. This project, the location is actually a big advantage because it's in the largest industrial region in the UK, which provides value by integrating the potential for both a decarbonized industrial hub and hydrogen economy, which is like an emerging economy that we have been talking about for some years now. And for sure, that brings us back to the idea of sector coupling. That's a big theme for decarbonization going forward. Next slide, please. Moving to the utilization piece, I just want to highlight there are like different opportunities to expand the utilization opportunities, whether at the technological scale or at the policy scale. So for the technological part, for example, catalyst and material development for conversion technologies into fuels and chemicals, that's a big research area that can expand the opportunity for utilization. Also, increased uptake of CO2 during carbonation of primary and waste materials for the production of different building materials, what we call like as mineralization process, and also increase the direct uptake of CO2 for polymer production that then can be a feedstock for different products and different industries. On the policy side, government procurement program can actually help a lot. They can commit to purchasing material that begin to utilize the captured carbon dioxide in their production, such as cement, concrete, aggregate, and also building codes and standards need to be updated so that they can accommodate these kind of new materials and allow for carbon dioxide-based products to be used. Next slide, please. As we mentioned before, the abundance of geologic storage here in the US can store like hundreds of years worth of industrial greenhouse gas emissions. Something we need to pay attention to is the injection rates when we talk about carbon storage, because they must be monitored during the operation and to the extent that they don't exceed the reservoir pressure or the cap rock formation pressure. And as I mentioned earlier before, we have established great experience with that in a way to make sure it's a safe operation. Next slide, please. I just wanted here to just highlight the example of this particular project, the Illinois Basin Decatur project. It took approximately 4.5 years to receive a Class 1 permit, which was then they needed to apply for a re-permit to make it Class 6 when it was, and the new category was introduced, and it has been the first well completely authorized under the Class 6 program from the EPA. And this process took nearly 5.5 years to complete before even injection could begin. So that gives you an idea about how the current framework can jeopardize the timeline of any large scale project, and that's something that we need to work on to allow more project developers to put some of these large investments. Last slide, please. Finally, I want to highlight that CCUS technologies have a dual role in climate change mitigation. First and foremost, they can reduce emissions from energy-intensive industries and power generation. And the second part is that they can be used for carbon removal from the atmosphere. While the capture part is different in emission reductions compared to removal, the transport and the storage part are actually the same, which is why scaling this kind of infrastructure is essential for the development of carbon dioxide removal technologies. I'm sure, as many of you may know, the recent assessment report of the IPCC have underscored the urgency to expand the use of carbon sinks to avoid the most drastic consequences of climate change. All mitigation pathways in that report use CDR technology to a certain extent, depending on how ambitious the scenario is. And you can see from the graph here, the potential role of CCUS technologies in these different scenarios to both reduce emissions and remove carbon. The National Academy of Science has reached the same numbers, or the same conclusion, that 10 gigaton of CO2 need to be removed globally by through 2025. 20 gigaton each year need to be removed from 2050 till the end of the century. And that is why building a carbon infrastructure now is essential to allow time for this technology to scale up and reach that capture and removal levels that we need to achieve decarbonization by mid-century. With that, I would like to thank you all for your time, and I'm happy to answer your questions later after our panel. Thank you.
Okay, Erin, take it away.
Thanks so much. I'm Erin Burns. I'm the Executive Director of Carbon 180. Carbon 180 is a climate NGO focused entirely on carbon removal. So really fantastic transition. I will talk mostly about direct air capture, the technological pathway. I want to share a little bit about what it is, where we are today, where we need to be, though Mahmoud covered that as well, and how we'll get there, as well as a few opportunities along the way. So I have a lot of slides as a heads up, but next slide, I'll be quick with them. They're mostly pictures. Mahmoud covered much of this, but just as a note, sort of, we all know global emissions are on the rise. We need to stop emitting, but really that's not enough. So next slide. We need to also go negative, and we need to go really, really negative, and sooner than folks think. So we need to be talking about removing tens of billions of tons from the atmosphere, and we need to start doing that now. Next slide. Luckily, we have lots of options to do that. So there are sort of natural pathways around soils and forests, and then more technological pathways, and in particular, direct air capture and bioenergy with CCS. We use the term carbon tech to talk about utilization outside of enhanced oil recovery. We don't really work on enhanced oil recovery. And so carbon tech is that kind of captured CO2 to products piece. Next slide. So where are we today with carbon removal? So there's a ton of removal potential across solutions. And one of the really exciting things about direct air capture, bioenergy with CCS, the sort of technological pathways, are that they can really, really scale. So if we're talking about 10 gigatons per year, they're going to play this really big role. But right now, next slide. I'm sorry, next slide. Oh, there we go. Perfect. They're expensive. They're the most expensive pathways, and in particular, direct air capture, which we think has the most scaling potential, or potential to scale without sort of unintended consequences, we'll say, that could come with land solutions or with bioenergy with CCS. Direct air capture is really expensive right now. So it's somewhere in the $200 to $600 per ton range. There is a lot of reason to believe that we can really bring down those costs even with current technologies, and then innovation can play an even bigger role in pulling those down, and then we could see costs in the sort of $50 to $100 per ton range. Next slide. And just to give you a sense of sort of current deployment of direct air capture, this is this is on our website. It's called our DAC map. MAP is an acronym, hence the spelling and capitalization. And if you look at the map here, this includes not just current deployment of direct air capture, but also research around this, locations of direct air capture companies. You can see that most of the activities happening in the U.S. with a little bit in the U.S. and in Europe, with a little bit elsewhere. And you can see this is pretty geographically diverse within those two regions. And there's sort of a lot of different things happening. Next slide. But, oh, actually, well, we can skip to this one. It's fine. Oh, sorry. But if you look at just actual direct air capture deployment and commercial direct air capture deployment in particular, not including demonstrations, you'll see that that number really drops pretty rapidly. And next slide. But we did have recently the largest direct air capture plant was launched in Iceland just this past month, the Orca plant from sorry, no worries. The Orca plant from Climeworks, which also has a facility in Zurich, so is responsible for most of the commercial deployment right now. I will mention, this is perfect. You can stay on this slide. You know, I will mention that there is a 1 million ton per year planned plant in West Texas as well, which would obviously obviously represent a sort of couple of order of magnitudes increase in the size of commercial direct air capture plants. So where do we need to go? Perfect. I just want to pull this back up again to reiterate, you know, we're really talking about, so the Orca plant that I mentioned is actually, it's our sort of largest DAC to storage plant, but is only about 4,000 tons per year. So that's a really big accomplishment for the technology. But what we're talking about, again, is really billions of tons in the next couple of decades. And one quick note, if you, next slide, sorry. You heard Mahmoud also bring up the 10 gigatons piece. To go more in depth on sort of the specific applications and the trade-offs and benefits that come with different carbon removal solutions, definitely recommend there's something called the Road to 10 Gigatons. It's a like very simple game online, basically, that really, I think, helps folks sort of get introduced to the specific carbon removal pathways. Perfect. So how do we get there? So one of the most exciting things I think happening right now in carbon removal, sorry, next slide, is that we have big corporate, more big companies like Stripe, Shopify, and Microsoft who are purchasing carbon removal. So this is very different than sort of where we've seen low quality, inexpensive corporate offsets. But instead, if you look at many of the materials, for example, that Stripe has published around purchasing direct air capture and other forms of carbon removal, you'll see that they're really interested in very high quality carbon removal that's very verifiable, and that they're very comfortable purchasing expensive carbon removal because they see the same sort of graphs that we see where we really need to scale up this industry. And so they're looking to invest in this. And this has been a huge catalyst for the carbon removal marketplace. Next slide. But when we're talking about billions of tons per year, companies are not going to get us there, and we need a lot of policy. Luckily, there is a lot happening. Most of this at the federal level, and most of this is at the federal level, but there are several state things like the low carbon fuel standard in California, some carbon tax procurement efforts in states like New York, California, Hawaii. But there are also major federal policies that are moving forward. The one that I will point out is actually there's $3.5 billion for regional direct air capture hubs. This would be 4 regional hubs across the US in the infrastructure bill. If passed, would be, I will say, I think starting in as recently as 2018, we had basically no federal investment in direct air capture. So a really massive change. So you can sort of see not just the scale of investment, but also the sort of speed at which it's increasing. Next slide. So I just wanted to I'll wrap up and happy to answer any questions, but I want to touch really quickly on the opportunities, since the first bit's a little really about how much it costs and how we have to do it and how far we are behind. But there are a lot of opportunities around direct air capture. One of those is jobs. So if we're talking about pulling billions of tons of carbon from the atmosphere, we're also talking about hundreds of thousands of jobs. So this is for 1 megaton plant, but across again, if we're scaling up in line with climate goals, we're going to see hundreds of thousands of these jobs. And these jobs are not just at direct air capture plants, but they're across other industries. So for example, if you're building a direct air capture plant, you also need a lot of steel to produce that. So you're talking about steel jobs and so on and so forth. And this is pulled from the Rhodium Group, did a really fantastic report about a year ago on this that I would highly recommend. Next slide. And then finally, around carbon tax, I'm going to also covered this, but or talked a little bit about the opportunities around utilization. But in 2018, we did a market sizing report around carbon tax, so that captured CO2 to products piece, and found in the US alone that there's a $1 trillion total available market across building materials, fuels, plastics, chemicals. And so this represents both an opportunity to create a market for that captured CO2, which is especially important for direct air capture applications. In a carbon capture plant, you are producing a product, electricity, or steel or cement. But in a direct air capture facility, it's really important to think about the fact that this is just sort of a public good. But if you are able to sell that that captured carbon dioxide, it's going to help offset the cost of the direct air capture plant. It's also going to help decarbonize these other sectors. So there's opportunities in building materials. We have a report on that I'm happy to share. There are opportunities around jet fuels and things like that. So a big opportunity, and then almost $6 trillion globally. I'll stop there, but looking forward to hearing what Amici has to say and happy to answer any questions. Thanks, guys.
Hey, should I just go for
Hi,
it?
Misha. Yeah, just go for it.
Awesome. I'll try to keep it real quick. Thank you so much, Erin. Thank you, Mahmoud. It's a pleasure to go after you all and after Dr. Esposito and Dr. Grubert, because I don't need to say as much. A lot was covered in the context of what CCUS brings to the table. So what I'm going to just try to highlight right now is what utilization technologies we're investing in and what the synergies are. I think there was a couple questions about how we're working alongside other DOE offices, but there's also a lot of opportunities for utilization technologies in the CCUS supply chain. So with that, I'll just try to speed through my one slide. So as Dr. Emily Grubert mentioned before, we did we reorged. We had a rebrand for fossil energy. It's now fossil energy and carbon management. I think she highlighted that we work on critical material. There's a higher emphasis on critical materials, DAC, CDR, including also utilization, but also industrial decarbonization and methane mitigation. I wanted to flag that things such as hydrogen production and critical materials also play a role in helping create this carbon tech economy. So what is this carbon tech or carbon utilization? I like to use this figure on the right just to kind of frame all of the current R&D thinking we have going on in the program. So you're gonna be the CO2 molecule, right? You're gonna be in the center. And you have a couple of pathways you can go down, right? These utilization pathways. Let's talk about the one on the upper left corner, algae or bioproducts. So this is a biomass, a biological uptake of the CO2. The reason we love biological uptake mechanisms is that nature has been consuming CO2 and transforming it into something wonderful, for the last 2 billion years, at least. It can create some of the most impressive compounds that, you can think of, pigments, nutraceuticals, and we've had a lot of experience in optimizing these systems from the biological perspective. The Bioenergy Technology Office in particular has invested billions of dollars over the last roughly 3 decades to really optimize the type of products you get out of these algal systems, whether they're micro or macro, like seaweed, and even in the oceans, not just in your typical ponds or your test tubes that might come to mind. So what is our perspective when we look at this problem that, lots of dollars have already been thrown into, lots of brains have already thought about? I think a very interesting perspective that we bring. And I think Congress was very smart in putting it in explicit language that utilization programs should spend money on these algal uptake systems, is the carbon efficiency is something that we haven't quite optimized, right? When you put in CO2 into these algae systems, sometimes there's off-gassing. They're optimized to create a product at the end, not use the most amount of CO2. So a lot of our projects that we look at within the portfolio, which is about a quarter of our portfolio, we really work on optimizing how we deliver that CO2, how much is stored, and thinking about products, not just to create biofuels, that's what Bioenergy Technology Office does, but really looking to sequester, to use and utilize and lock away as much CO2 into the final product. So in some cases, that means you don't post-process, right? You have animal feed, bioplastics. There's a variety of products beyond biofuels that we invest in. Moving down, we'll talk about mineralization. So CO2, I call the Monday of molecules. I've been trying to get it to happen for some time. It's not like a very catchy saying, but I think it's true. It helps people understand CO2 is boring. It's really hard to work with. No one enjoys it, but it can get more boring for most people. CO2 can become a rock. I'm a geologist, so shout out, Richard. I'm sure you're like, rocks are interesting. Rocks are interesting, but only in certain cases, right? For us, the rock is interesting if that rock could be used, especially in a product. So what we've investigated thus far in the portfolio is using this mineralization, this rock creating capability of CO2 in building materials, explicitly concrete. Concrete, just so we're all on the same page, is the mixture of aggregates, that volumetric rock that you put into the concrete block, and cement. Cement is pretty much the active ingredient, the binder that latches onto the CO2, usually from the atmosphere, and creates a carbonate, creates that rock again and locks everything into place into that concrete cinder block. So what we've worked on in the program thus far is a pretty plug and play into the industry technology solutions. We wanted to optimize and enhance the amount of CO2 that gets pulled in during that curing step. A couple of our projects have been able to scale up quite quickly compared to others. Carbon X Prize actually awarded was one of our projects was a co-winner for the Carbon X Prize. It's the carbon built technology coming out of UCLA. And that really looked at taking these precast, CMU blocks and bringing in flue gas and making sure it flowed right. We had the right relative humidities, the right temperatures, and really maximized the amount of CO2 that was locked away. Looking forward, I think something that is a really good, interesting space for us to work on is synthetic aggregates, creating that volume that creates a carbon sink potential for carbon utilization or carbon tech products. It offsets a very carbon emissive process that's in the broader cement industry and concrete industry. So what you're replacing and displacing the market is of benefit as well. Finally, other areas that we're looking at in the next generation concretes are also looking at composites. How can you have CO2 derived carbon fibers? How can you have second generation concretes that are maybe a bit more flexible, the ones that self-cure? These are all benefits that we're seeing with our emerging R&D technology in the mineralization space. Moving over to our last conversion pathway is something that we just deem conversion. It's called conversion because it's just kind of a catch-all. Really what we are looking into this pathway right now is a pretty simple recipe. It's CO2 plus some energy, usually some reactant of some sorts. This is the tie into hydrogen, right? Like if you want to create a compound, you need to get that hydrogen source. So we can have CO2 plus hydrogen, and usually you'll need some catalysts, right? If you start hitting CO2 with energy to try to break those bonds, you want to be really selective with the bonds you create afterwards. Our conversion pathway is a lower TRL pathway, lower technology readiness level. So these are the emerging technologies such as electrocatalysis, electrochemical reduction, right? We're taking the same system that's a fuel cell, that takes in fuels and creates, electrons in, say, water. We want to run it in reverse, in essence. So you're going to be giving it electrons, you're going to be giving it, in essence, the waste products of CO2, and you're going to recreate that chemical energy into that organic compound. You're going to be creating fuels, you're going to be creating chemical monomers, formic acid, ethanol. Hopefully what you're seeing here is that unlike the algae pathway, unlike that uptake pathway, this catalytic conversion pathway sometimes, or has predominantly, yielded smaller molecules, right? Formic acid, ethanol, these are little cute carbon molecules, 1 or 2 carbons connected to each other, because creating that carbon to carbon chain, that connection, takes a lot of energy. It takes a lot of specific catalysts to make sure you're creating that same structure. So there's a lot of work to be done. It's probably one of the more exciting spaces that we're funding, because there's so many people interested, because there's so much room for growth. Other areas that fall under this catalytic conversion of sorts are plasma mediated conversion pathways. We have obviously a lot of thermochemical, that energy source that you add in is heat. And we have really interesting hybrid systems as well. Perhaps we have some that use electrons to actually power, like, bioorganisms to convert the CO2 into new products. There's other areas of growth right now. We actually put out a lab call to a couple of national labs in our network to, instead of using say pure CO2 or CO2 from the atmosphere, rather, we were hoping to directly capture and utilize the CO2 in the same step. So this was a reactive capture and conversion lab call. The reason why this is interesting, right, is now you can co-locate CO2 potentially with DAC or with smaller sources, ones that may have not been economical to deploy a whole capture system, or in areas where you may not have viable storage, as was mentioned earlier. Having a system that is intensified and can do 2 steps all at once to create a product that's easier to store, easier to transport than pure CO2 is also a wonderful potential. I think there's a really promising project that we have out in Pacific Northwest. And what they've done is they've actually looked at that electrochemical system that I mentioned before. And instead of feeding CO2, they're feeding loaded capture solvent. So this also gives you the added benefit of coupling, not maybe just with a DAC, but maybe with a conventional capture system, and offsetting that parasitic load to create, a product, rather than just regenerating CO2, or, it's a different, less energy intensive way to regenerate your capture solvent. So there's a lot of opportunities and a lot of technical space that, these solutions are working towards. I also wanted to highlight, or unhighlight, I guess, this physical services pathway. Currently, the portfolio really doesn't really doesn't look at EOR or working services for CO2. That's predominantly been done in the carbon storage program. Sorry, I said I'd be quick. I'm trying to close out. I think the other things worth mentioning would be, we have a very good LCA life cycle analysis. It's actually was referenced in the 45Q in the preamble. We've used it to really evaluate R&D across these platforms, and we're really excited to be working with National Carbon Capture Center, and we've done a little bit of testing there. So yay, there's been successes all around. All right, I'm definitely done now. Thank you, Eddie.
Thank you, Mishy. Appreciate your information and insight. So we do have a question from the chat box. With the current and projected cost of direct air capture, why not invest that capital in capturing existing or legacy emissions?
Yeah, thanks so much for that question. So I'll say for us, we don't work on point source carbon capture, but I spent a lot of time in my previous jobs working on this. And I don't think it is an either or. I think you really need to invest in both. And I think, first of all, as my fellow panelists have pointed out, there are opportunities, sort of shared R&D opportunities. There are, when you're talking about the actual CO2 capture, there are some differences in the technology, but there are some overlapping sort of R&D needs. There are also a lot of shared infrastructure. So what you do with captured CO2, it doesn't typically doesn't really matter what the source of it, if it's direct air capture or point source CO2, so that utilization piece, things around storage, direct air capture has a lot of flexibility in where it can be located, but it can be located anywhere. There are still transportation needs associated with that. So things like shared infrastructure. And then I think the other thing I'll say is that, we talk a lot, I think in the CCS world about the places where you need CCS to decarbonize, where it's really expensive, or the technical feasibility of decarbonizing certain industrial applications is that's just really difficult right now, if not just outright impossible or too expensive. But I would add to that, like, if you look at things like carbon, you just need carbon removal, like maybe, in my opinion, maybe a little bit more than CCS, in the sense that it's, this is your way to address legacy emissions. So we already have too much CO2 in the atmosphere. We are continuing to emit CO2. And so the only way that we really have to get rid of that is carbon removal. And there are a bunch of reasons I think it's important to consider direct air capture and other technological pathways, and not just land-based, but I think that this audience probably understands that already. So I actually think it's important to really invest in both, but it's absolutely essential for us that we invest in direct air capture right now.
All right, thank you. Let's say that a state wants to start a discussion and the development of a CCUS project. What infrastructure needs to be in place to begin that development? Open for anybody.
Yeah, I would say storage is really important element, because before you start thinking about capturing carbon, you need to make sure that what are you going to do with that carbon that you're going to capture. So the availability of a pathway for the capture carbon is mostly important. And for sure, from an environmental perspective, the permanent storage is the highest benefit. So we have a problem with the commercial readiness of storage sites, not just in the US, but at a global scale, even though we have the experience to do that. So that's an infrastructure element that we need to work on. The other elements, whether it's the capture, as we discussed, the capture part, the technology is there, even in its, for example, like oxy-combustion is embedded in different industrial processes already. So you don't even need to train your staff or your crew on how to do that part. They know it's, or they get most of it. So that wouldn't be the hardest part. The transport part or the storage part is the biggest question mark when it comes to the decision. And they're also the most energy and financially intensive.
Yeah, the only thing I'll add from that is I think there's actually a really helpful sort of direct air capture example, which is, I mentioned there's a couple of plants, but one of the first one really was outside of Zurich, and it was placed on it was placed on top of a waste energy plant where they could get waste heat. And it was placed next to a greenhouse that had a CO2 pipeline already there. And direct air capture, I think, is helpful as this example where it's, you can talk about a really small scale, but it is very expensive, but the opportunity there is to go and say, what is the site that already has that infrastructure in place that is going to enable us to move quickly on this, that is going to lower, the CapEx. And so I think there's a similar thing if you're looking sort of statewide at opportunities around carbon capture, finding those places. Like if you look at carbon capture deployment now, as Mahmoud said, it's like not at the scale that we need, but it's actually in like really specific, you'll see like certain industrial applications have a much higher rate of deployment. And you see this in these niche places where you just have sort of both the existing infrastructure, the technology is there. You have all of these different pieces of like, how pure is your CO2 stream? And do you have these pipelines nearby? And do you have the energy you need? Or what is the parasitic load and all these pieces? So I think there's like several things. The thing I will add to this is there's really interesting work happening at NETL. And I was just talking to a researcher who's doing between there and Carnegie Mellon around helping facility operators sort of understand what it would look like for their facility. So I think there's some really great stuff coming out of DOE around making this like much more tangible.
And I think the only thing I'll add, because we can, talk at length about the technical perspectives, and that's usually what I highlight. But I think something that DOE has really been great about in this administration is changing not just technical, but looking at the environmental justice implications, considering all those, community outreach. And I think that's something that's been lost in the conversation previously, and it's like awesome that we're highlighting it now.
We have time for one last question, and the question is from Mississippi. Can you describe some of the characteristics of permanent storage? We've talked about permanent storage in that term, but what does that mean? What are the characteristics?
So yeah, permanent storage means that you have a reservoir formation that can trap the carbon dioxide there over a geological time scale. So the condition for that is that this particular formation has high permeability, but there is another cap formation above it that has very low, almost zero permeability, which traps the carbon dioxide within that reservoir formation and prevents any further movement. So as you inject the CO2 in the reservoir formation, for sure, like following a certain pressure that you don't exceed, so you don't cause cracks in the formation and you don't increase your injectivity limit and stuff like that. Once it's down there and it's capped by this cap rock, it stays for thousands of years. And this is actually, we are just imitating the naturally occurring reservoirs. That's how oil and gas or other hydrocarbons happened over like millions of years. They are trapped down there under this high pressure with impermeable formation. So what we are doing here is just we are imitating nature, and we have been doing that for thousands of years. Like, I mean, the nature is doing that for thousands of years. We are doing that for at least, I would say like 50 or 70 years, the last 70 years at least. The oil and gas industry has been doing that, whether with CO2 or with other things. Like even when we talk about EOR, you can do enhanced oil recovery with other sources, not necessarily CO2, but if you have the opportunity, in relative terms, using CO2 will make your barrel of oil has less footprint. So that's an example.
Yeah, I'll just add really quickly, you can check out USGS has done some really fantastic mapping. We have a ton of saline formations in the US that are great for storage. DOE has stored a few million tons of CO2. The big challenge here is actually, I think other folks hit on this, is around the regulatory program and sort of resources that the EPA has to permit these. That's really one of our major challenges here. But this is something that, like, yeah, we know how to do it. We know how to do it well, and there's great opportunity in the US.
I'm getting the hook. I see Kirsten on the screen. Mahmoud, Aaron, Amishi, thank you for participating on this panel. Is it okay if state officials want to follow up and get in contact with you to learn more?
Absolutely.
Yes.
Perfect. Kirsten, I'm going to turn over the session to you now.
Thank you so much, Eddie, and thank you to our excellent speakers. And if anybody wants to get in touch with them and doesn't know how, we're happy to facilitate that from NASEO's side as well. Sorry. And I just wanted to announce we have a quick break, 10 minutes until 3 p.m. And then we'll have a final session on CCUS projects, kind of how did they go from the drawing board to implementation. And we have an excellent lineup there. So please come back at 3 p.m. After the break, and we'll close it out with our final panel. Thank you. Hi everyone, I would just like to welcome everybody back from break. I'm really excited about the next session. We will look at some of the CCUS projects underway and how they've managed to get from the drawing board to implementation. And I would like to turn it over to my colleague Rodney Sobin, who's the Senior Program Director at NASEO and who will moderate the panel. Rodney, over to you.
Thank you very much, Kirsten. Welcome back, everyone, for this next session, from drawing board to implementation, support for CCUS projects. This will focus on how, as the technology becomes more mature, projects will need to move from the demonstration and conceptual and pilot stages to wider scale deployment. What state and federal support and partnerships are necessary to do this? And what lessons can be learned from projects underway or under development? So this panel will explore these questions. We are very fortunate to have Eugene Holubniak and Shannon Mikola to join us today to share their experiences in developing CCS projects. They are highly experienced, bringing to bear technical, economic, regulatory, and legal expertise needed to develop these complex projects. They really are truly leading the path forward on CCUS. First, you will hear from Dr. Eugene Holubniak, who's a petroleum engineer at the Kansas Geological Survey. Previous to that, he had worked for a few years at the Plains CO2 Reduction Partnership before going to the survey in 2012. He's managed various research and field scale projects funded by DOE, and participates in multiple projects as co-PI. Currently, he serves as a joint PI for Carbon Safe Phase 2 Integrated Mid-Continental Stacked Carbon Storage Hub Project, which is quite a mouthful and probably not pronounceable as an acronym. I think you had heard earlier about the Carbon Safe in our opening discussion. He also leads the Kansas CCUS Task Force and represents his agency in the Regional Carbon Capture Deployment Initiative. He specializes in reservoir modeling, simulations, and fluid geochemistry, and is very familiar with and working on UIC, the Class 6 well issue. He will be followed by Shannon Mikola, who is a graduate of Colorado State University and received her JD with honors from the University of Wyoming Law School. She joined Minn Kota Power Cooperative in 2018, where she has two roles: Special Project Counsel and Carbon Storage Facility Lead for Project Tundra, which you will hear quite a bit about in a few minutes. She's leading development of Project Tundra's Class 6 storage facility, which currently is the largest geological storage application ever filed in the United States. She leads teams of external consultants and field crews who conduct drilling, geophysical surveys, subsurface technical expertise analysis, and pore space leasing needs for the Class 6 application. So again, combining technical, economic, regulatory, and legal aspects. Prior to joining Minn Kota, she was with the firm Kamrud, Maddock, Olson, and Larson, and served as an academic affairs officer at the University of North Dakota. She was honored to be selected as one of 20 winners of RE Magazine's first ever Co-op Rising Stars contest. So I will hand it to Eugene and rely on one of my colleagues to put the appropriate slides up. We will try to reserve time for Q&A after both presentations. Thank you. Take it away, Eugene.
Well, thank you for this opportunity to present in front of you. I have some technical difficulties today, and I have to connect from my cell phone, so I apologize about this. At the same time, I do have slides, and we probably can go for this. But since I do have only about 12 minutes to go for my slides, I'll probably just kind of shoot from the hip and explain kind of the main obstacles for CCUS and going forward, because also looking at kind of lessons learned from this previous sessions today, I'll kind of outline a few issues that can make it difficult for the projects to go forward. I also agree that the basically developing industry is developing CCUS CCUS industry has a lot of acronyms and it is a mouthful. So I'll try to stick to simplified version of those terms, or basically try to be as simple as possible, not to complicate things around. And so there are several major obstacles for moving things forward. It is understood, why we need the CCUS. There are lots of large point sources. There's also potential for direct air capture, of course, and the rapid development of renewable energy, especially here in Kansas. We do see as wind is picking up. We have, depending on when you are measured, but it's anywhere from 42 to more than 50% of all of our power generation here in Kansas is happening from wind resource. And so, but at the same time, we do have this baseload capacity with power plants that are using coal and also natural gas and some other fossil fuels as well. And so it would be a waste if you let it go. So also we understand the resources that are necessary to store carbon. And as mentioned in previous sessions, we went through the exercise and we characterized a number of those resources, and there are sort of soft and hard criteria on how you select or disqualify sites from moving forward with the CO2 storage. So we know all those things. There's also oil and gas industry that is here to help, basically to facilitate many of those things, including enhanced oil recovery. And so also, if you do retrofit a lot of those power plants, as is being discussed currently, from, let's say, coal power to, let's say, hydrogen generation, a lot of those will still need CCUS, and so you will end up needing all this infrastructure and all this development for those technologies to store carbon. So this is why we care about this in Kansas and in region in general. So if we move to the next slide, we also looked at we characterized those resources not only from geological standpoint but from engineering as well. We connected with the number of coal-fired power plants, but also with ethanol plants and with other CO2 generating facilities like fertilizer plants and refineries. And so there's a scale of complexities for each facility, as always. And so with easiest plants being ethanol plants, and with the hardest plants being probably things like cement and steel producing facilities. And they all will need cement as well. They all will need carbon capture on them. And so there's a question. So what do we need in order to move projects forward? One of the things that we need is an infrastructure. And the infrastructure means not only CO2 storing facilities and not only capture facilities, but also connecting the dots, because a lot of times sources and sinks, unfortunately, do not coincide. And so you can have a power plant that is kind of sitting in unfavorable geologic conditions. So basically, you don't have a storage facility. You cannot make a storage facility next to this plant. And so what do you do? Also, if you want those projects to be sustainable, and if you want sustainable industry, this is another reason why you might need this infrastructure. Because in order to move the CO2, if CO2 becomes a product, if you can make products from the CO2, you will need this infrastructure. And so connecting sources and connecting sinks is imperative for moving forward. Also, you can later on you will add probably other gaseous components to this infrastructure, because there is also hydrogen economy that is coming. There is also things that from which you can make hydrogen, like ammonia or ethane, if you're talking about sort of blue hydrogen technologies. And so it adds the complexity, but it also asks for the infrastructure. The next big big item is in order to permit storage facilities, like we researched with the help of DOE, you need the investments from those companies that are willing to do the CO2 sequestration. However, a lot of times this investment is not for sure. Because yes, we can, as a Kansas Geological Survey, we can advise our stakeholders on where to drill, what are the most favorable locations. Yes, we do have this information, but even with this information, as we learned from our experience, not all geological sites are made equal. Because in some cases, you do have intelligence on this particular structure, and you kind of have a guess that the structure can store a lot of CO2, but then you go ahead, you drill a well, and then you drill another one, and then you find that you actually don't have that much permeability, and you cannot squeeze as much CO2 as you thought you could into this formation. And yet another structure, basically down the road, very near to where you drill the well, just like oil and gas, is actually an excellent facility. And so in order to do this, you need more research, you need to drill more wells, you need to understand regional trends, regional geological trends. And so a little bit more investment would help actually to move those projects forward. And why don't we have this information? The reason is that oil and gas information that we have from the reservoirs is present in abundance. We have a vast database of oil and gas wells, but those oil and gas wells oftentimes don't penetrate all the way through the geological strata, through the sedimentary layers. And so we don't have the full picture of what kind of resource is available. And we're still finding those new sources, kind of like we find oil fields, we find those new sources, the pore space resources for storing CO2 and actually other fluids in Kansas, although we thought that we actually learned about everything, but no, actually there are some certain basins that are still kind of undiscovered. And so more drilling and more geological characterization, engineering characterization to move projects forward. More of that is needed. The next question is permitting. And so USC Class 6 permit is complex. It has multiple caveats to this process. And as one of the individuals who went through the process, I can tell you kind of insider information about this, is that it takes a long time because it has multiple kind of chains of command within the EPA. And so your information that you provide to the agency is bouncing through different specialists, through consulting agencies, and so on and so forth. And simplifying this process and also providing EPA with necessary resources is probably required to move projects forward. Because from the investor's standpoint, this is a big risk. And a big unknown. If the project cannot move forward in, let's say, 1, 2, 3 years, the investment could be off the table. Multiple companies, and I'm not going to name names, but working with advising multiple projects, commercial projects right now, are struggling with investors because of this unknown variable, which is the length of the permitting process. And so if you can make sure that you have a decision after a certain point, and if you can shorten this decision period, you can make sure that the investors are actually willing to invest in those projects going forward. And then there's another big question, and it's also about legislation and regulatory framework, and it has to do with pore space issues and liability issues. So we don't, in some states we do, in some states we don't. In Kansas, there is some ambiguity about who owns the pore space, and can you actually condemn the pore space to make the large scale project? Because In certain cases, it is possible, especially if your project is not a large-scale project, like some of the ethanol plants that are injecting above 100,000 tons of CO2 per year. It's not a large amount, and so it's not a big issue. But if you want to inject millions of tons of CO2, and you need a lot of space, then it could become a big problem. So these are kind of the main issues that we see, also primacy for, and I'm pretty sure Shannon will talk about this in more detail, but primacy for USC permits is essential for moving projects forward in different states. And so at the moment, it is only North Dakota and Wyoming, but there's also Louisiana working, and they're very close to get the permit in. But I think we need more states that will have USC Class 6 primacy for the projects. Well, I think that concludes my part, and I'll take any questions later.
Thank you, Eugene. This is very helpful. We'll have questions for Eugene later. Let me hand it over to Shannon for her presentation. Take it away.
Thank you. Thank you for the invitation to speak today a little bit from the perspective of Project Tundra. I do have there's a short video that kind of sets the table as to what is Project Tundra and its significance to Minn Kota. Not sure that there's any audio coming through, and if not, if we can get the audio to work, I can just, the slides I have can kind of set the stage for that as well.
Give us 1 second, Shannon, to potentially work out the audio issue.
I can hear the audio on my end, so maybe we should just drop the link in the chat, and if you all want to check it out after, we can move forward with Shannon's presentation. I'll try one more time.
And back in the 1930s and 40s, we worked together.
Works now.
Brought rural electrification to communities who didn't otherwise.
Kelsey, if you unmute yourself, we can hear the audio.
We need to tackle.
We're willing to have some guts to try something new. We can continue that spirit as well as allow for technology to get advanced and that benefit our region and our members. That's what we're supposed to do.
The time is right now. We need to develop those technologies now for those existing plants and the plants of the future. We need to work as hard and as fast as we can on developing technologies to reduce the cost of carbon capture.
Project Tundra is an effort on our part to try to figure out how to capture carbon dioxide off the backside of our largest coal plant. And we're doing that to try to figure out how to reduce the CO2 footprint of the generation that we provide. And it works basically by running the flue gas, or the gas that comes out of the plant, through a scrubber that will pull the CO2 out of it, remove it, concentrate, and allow us to store it permanently in a safe spot.
Project Tundra facility is being designed to capture 90% of the CO2 from either generator at the Young Station, which is about 4 million metric tons per year. And another way to think about that is it's about 800,000 gasoline-powered vehicles being taken off the road every year. And another way to think about that is it's roughly all of the vehicles registered in the state of North Dakota.
Yeah, so at the EERC, we've been working on carbon capture, utilization, and storage since about 2000. So we have a long history, partners as well, of understanding how you would inject carbon dioxide and how to do it safely and effectively.
once the capture equipment is installed, CO2 will be captured at a rate of roughly 4 million tons per year. That CO2 is compressed and then transported by a short pipeline to injection wells that will push the CO2 into formations, geologic formations, in the order of 5,000 feet down to as deep as 10,000 feet below the surface. At those depths, there are various geologic formations or horizons that are prime targets for taking the CO2 and storing it safely and permanently.
You need these porous sandstones that act like a sponge and suck in the CO2. But not only that, you need these unporous or the impermeable caps and basement rocks above and below these porous materials that will lock the CO2 in place.
Milton Young sits right on top of a great interval of these types of rocks. Groundwater in and around the center comes from less than 1,000 feet down. Storage of CO2 in that area will take place at depths around 5,000 feet up to 10,000 feet. Between that aquifer that people are using their water from and the shallowest target that we're going to put CO2 is thousands of feet of rock in there that's very good for keeping CO2 in place. So the risks are very negligible with respect to any impacts to the groundwater.
We are at a very exciting time. We're right at the cusp, right at the precipice of an explosion in the concept of carbon capture. There is no way for the world to meet the goals that the IPCC has set for CO2 concentrations without carbon capture.
You can add a substantial amount of renewables to the grid, and we are, and in the US, you'll see that number climbing. In our region, you'll see it climbing. In Minnesota's case, we have a substantial amount of renewables in our portfolio already.
We need to have resources at our disposal to keep that grid reliable. Coal is a part of that strategy. We also have to have other energy resources at our disposal, and it all has to work together.
The countries around the world that are just now industrializing, it's going to be important to raise them out of poverty, to give them access to low-cost, reliable power. And fossil fuels are by far the best way to get that done. The problem that people find with fossil fuels is carbon emissions. And we have the technology with carbon capture. Let's use our brains, let's use our technology to solve the problem.
And everybody wants to leave the world in a better place than what we inherited. And these are the types of projects that enable us to do that.
Because you know there's a real purpose for what you're doing and why you're doing it. And at the end, say to my kids, my friends, and neighbors, I was part of that. That's a big thing.
There's too many people who need what electricity brings them around the world for you to see fossil fuels go away. And so the pioneering part, I think, on our part, is just a natural extension of who we are and what we do.
Thank you, Kelsey. You can, advance the slide. So in short, I mean, that video really sets the table, I think, from the standpoint of what Project Tundra is about, and for Minnesota in particular as a sponsoring entity, why we continue to pursue it. But from our membership standpoint, as a GNT, we really view the need for firm resources in the current environment to be essential to our membership. And the Milton R. Young Station, Young 1 and Young 2, really do provide that reliable generation that we need. It is not uncommon in North Dakota and in northern Minnesota, where our membership are, that we experience negative 30-degree cold snaps. What we're seeing more of in recent years is the distance over which those cold snaps are extending, these polar vortexes that are impacting the regional integrated system operator areas. And so this is just a quick slide to highlight, the real motivating factor for keeping some of these coal-fired assets online. When you have a max generation event like we did back in 2019, the polar vortex, and there was a smaller one in 2020 as well. And, you can look at ERCOT and the event down in Texas as other good examples for, firming and, creating some resiliency across our transmission systems through hardening some of our generation assets. It becomes essential to consider CCUS as a solution to that, and to continuing to maintain some fossil energy on our grid systems. So very often, even though we have a wind nameplate in the 500 megawatt standard, we don't see that generation, and in particular, we don't see it during very cold times. Those wind turbines are not designed to operate at sub-zero temperatures. Once they get down around -15, they have to be shut down, and then they actually start drawing load to keep the gears and the lubricants heated so that they don't break. At that point, we really are reliant on our fossil-based energy resources to provide that load to our membership. You can advance to the next slide. So as the video there explained, Project Tundra is a retrofit to our Milton R. Young station, units 1 and unit 2. The design that we are currently looking at uses gas boilers to raise steam for the process, and that flue gas from the natural gas boiler system would also be routed through the CCS system. So this is just a flow diagram of the carbon capture technology process. This is an amine based, so it's really a heat transfer process to bond amines to the flue gas. So the flue gas enters the quencher, which brings it down in temp. Then you have the absorber where the amine solvent dredges our flue gas. And that CO2 rich solvent then enters into a regenerator where it's heated using the steam from the natural gas boilers, and the CO2 then pops out of the amine solvent in a 99.9% pure CO2 stream. It then enters into a compressor, which compresses it down to about 1700 PSI. One of the hurdles that Eugene mentioned is, you got to hit the jackpot in geology if you're a source close by, or we need to find ways to consolidate and transport. Luckily, Minn-Kota did hit the geologic jackpot. We only require a quarter-mile pipeline from the Milton R. Young station to the injection sites, which sit just south of our Milton R. Young station within our fence line. Advance to the next slide. So where we are in our carbon capture development, so front-end engineering and design study that was completed in June of 2021. We're now focusing on cost estimates and construction execution plan and schedule. So really finalizing that FEED design and engineering. Permitting is currently in progress for our air permits. Water appropriation has already been secured, and our discharge permits are in application, as well as our waste permits. We're in the process of transitioning into an EPC phase of the project, where we'll do final detailed engineering and design, enter into contract negotiations with the technology provider and any contractors that we might have on site. Okay, you can advance. So this is a rendering of what the plant is, and if you'll note up in the upper right-hand corner there, those two towers are exactly where our Milton R. Young 1 and 2 current chimneys are. There's a duct from the coal units down to the quencher. There's a duct coming from the gas-fired boilers that are sitting just below those chimneys at the Milton R. Young station. Flue gas moves into the quencher through the absorber into the regenerator. You have your process building and your compressors, water treatment and cooling towers. From a scale standpoint, the carbon capture system sits on the same size acreage as our current Milton R. Young station. So it's essentially doubling the size of the footprint. So that just kind of presents the scale and the timeline of construction. It's quite significant. You can advance to the next slide. On the geologic storage side, that map on this slide here shows our storage facility areas that we're currently under permit review for. And it shows the area of review for both the Deadwood and the Broom Creek, which are 2 formations. So quite a significant amount of characterization goes into developing one of these Class 6 permits, as Eugene mentioned. That's a huge hurdle from an economic standpoint for a lot of projects. We were lucky to be able to have some funding from the state of North Dakota, as well as through the Carbon Safe program, to drill and benefit from the data that was collected from the drilling of 3 stratigraphic test wells in and around the area. We performed 2 3D seismic surveys over this area, performed 1 injection test on one of the stratigraphic test wells. We also benefited from some carbon safe funding and, again, NDIC funds going towards the modeling, build out, and the simulations that we ran for the operation. We are fortunate, again, the geology ended up turning out far better than even was anticipated by the geologists at the ERC. And we're able to reduce the size of the project from a 2-site to a 1-site injection operation. We're pursuing a stacked storage concept with the Broom Creek at about 5,000 feet serving as our phase 1, and the Deadwood formation at about 9,000 feet serving as our phase 2 of operation. We are at over 80% pore space secured in North Dakota. We have very clear ownership interests in our statutes as to who owns the pore space and who we need to contract with for the rights. That has been very helpful. And then our permits for storage, our Class 6 and our storage facility permits, as well as drilling permits, were submitted back in May of 2021. Our MRV is finalized, and we are getting geared up to actually file that soon and get it in queue. Okay, you can advance to the next slide. This is really my last slide that I have. It's just kind of a current status of where our schedule and what are our next steps. So we're looking at, I think the key factors are we're looking at entering into an FID decision starting early next year, having a finalized EPC in late 2022. And because of the size and scale and the weather up here in North Dakota, it's something less than a 4-year construction timeline, but we're looking at it about at least 3 years of construction. So yeah, I'm happy to answer any questions about hurdles or barriers.
Great, thank you so much, Shannon. That was very interesting, and Eugene's as well. And I invite people again to enter questions into the chat and into the Q&A. We'll start with one of the Q&As, which is, what financial mechanisms are most helpful for commencing these projects, getting them off the ground? There are tax incentives, there are loans, there are credit enhancements. We've heard about 45Q quite a few times. And how might these differ, for different sort of actors? Shannon, you're with a cooperative utility, so you're a nonprofit, so tax measures may have a different flavor for you than for an IOU utility or an industrial entity.
Yeah, so for us, being a rural electric cooperative, we're a nonprofit, so we cannot take advantage of a tax credit. We are going to be dependent on tax equity investors in order to monetize those tax credits to pay back the capital expenditure for the build out of Project Tundra. To get this project off the ground as we're moving forward, certainly the grants from state and federal governments have been extremely helpful. Our membership being supportive of this type of project and this direction is also, very helpful from a sponsor equity standpoint. They have, Minn Kota has put up their own funds to match and to start, building out the development of this project. I'd say, when you're having to deal with big banks, they're going to see risk and they're going to price that risk at a certain level that makes it extremely thin margins in order to make $50 per metric ton work. The technology and the process itself on a per ton basis comes in at under $50 per metric ton, but when you add in the expected return for a tax equity investor, especially because this is a new industry and a new tax equity opportunity for most tax equity investors, they expect returns a bit higher than what they're receiving in, for example, a wind deal or a renewable deal.
Okay. Before turning to Eugene to get his view on financial mechanisms, I do want to tag on another question specific to your project, to Project Tundra. What are the anticipated costs per ton of CO2 captured, transported, and stored for the project?
Yeah, you know, at this point right now, I mean, if I factor in the investment return and the investor return and expectation, or the monetization rate that we would have to pay for those credits to be monetized, we're coming in right at about $50 per metric ton, making the project go. And that would include, you know, the price we're paying for pore space, transport, and capture.
Okay. Eugene, did you have any comment on the question about financial mechanisms?
Well, to add to the financial, because it is difficult to actually for projects to seek financial investments, because there's no direct pay for the 45Q, so they cannot expect the revenues, and especially for cooperatives or small, you know, like some of the ethanol plants, because ethanol plants notoriously they don't have high revenues and high tax appetite. So they have to go for the investors and bringing banks or hedge funds we've seen and other entities that with high tax appetites, and that's the only way to make it work at the moment. The problem with that, it's overall cost of the project, of course, is rising because of the margins, because of the what you have to pay to your investors back. So it is really difficult to, if you would like to eliminate this kind of third additional company in this chain, then you'll have to move to the direct pay option. I don't know how to do it. I'm not expert on policy on the full 45Q policy and how to move forward. But what I know, there are currently some proposals to make it happen.
Okay, great. So a question on regulatory issues. What are sort of the main regulatory issues that can hinder these projects? And for those interested in deploying CCUS projects, what regulatory barriers should they be prepared to deal with? And I will tag on to that. There had been discussion about the issue of the state primacy on the Class 6 wells. If as sort of a tag on to answering that question, if you can speak more tangibly as to the benefit of state primacy rather than sort of theoretically.
Sure. I mean, it's say it most often and lead with, I don't think Project Tundra would be as far as it is in its permitting process or development without North Dakota having primacy, as well as the strong support that we see from our legislature and our delegates here in North Dakota. So primacy by far has been instrumental, just from a timeline standpoint in and of itself. The example being, we filed back in May and we have our hearing on our permit set for November. So very quick review, a lot of opportunity as we're going through the characterization process to pick up the phone, call our agency and say, hey, we're struggling with this. We're having a hard time understanding whether this will meet the rigor of the standards. What do you think? Just a lot of collaboration and opportunity to have that back and forth that I don't think you get when you have to call a regional office to get those answers. There's oftentimes a lot of delay and through no fault of their intentionally. I think it's just short staff, short funding, and having to deal with a larger number of states and stakeholders really at the EPA level. So having it at a local level, you're kind of a little bit more the master of your own destiny from a permitting standpoint. I think some of the hurdles with any new process of permitting and a new concept is you start to catch the gaps or some of the doesn't quite fits with our project. And so there is that, real interest, I think, if you're creating the regulatory framework, to think broadly about all of the different types of projects that are currently in process today, but also into the future. What might be emerging technologies and how might those fit with your permitting regime?
So beyond the Class 6 issue, you had mentioned water discharge and waste permits. Are there particular concerns there, and are there issues with siting? Although I guess in your case, you're fortunate in that you have the geology very close by, so it's maybe less of a hassle than maybe some of the projects Eugene has dealt with.
Yeah, I think Minnesota's got, as a GNT, we have a lot of familiarity with air permitting and emissions, permitting through our state DEQ. I think, from the regulatory standpoint, if there is that, drafting of rules for this type of industry, it would be very important to coordinate with those other offices to understand what are their timelines, what are the coordination requirements, maybe review and consult periods that you'd want to see. So our North Dakota Oil and Gas Division, when we file our Class 6, it goes into a review process with the DEQ. And largely because part of the Class 1 wells are under their domain, and so they have some subsurface expertise. So there is that coordination between those offices. And so I think that can certainly benefit projects if there's a coordination effort on the part of the agencies to understand jurisdiction and where will the pipeline fall? Will it fall within, the Class 6 permitting regime as we're looking at storage facilities, or will that fall under, a public utility jurisdiction for transport? So having some of those questions sort of thought out and the interconnected nature of these projects, I think would be very important to spurring and knocking down some of those hurdles for developers.
Eugene, do you have some comment in this area regarding regulatory impediments?
Well, investors don't like uncertainty. That's the main. I mean, they deal with uncertainty all the time, and they try to eliminate as much of it as possible. And therefore, if they have more uncertainty with regulations, and some states not as advanced as North Dakota or Wyoming have some ambiguity in the regs, the more uncertainty you'll have, and the more problems you'll have with attracting investments, and also the cost of the investment as well. That's kind of my main comment on that.
Okay. We're getting close to time, but I do want to sneak in sort of a combination of two questions that came in. One of which is, what are key planning and coordination elements that are needed when projects are still at an early stage? And then what are recommendations that you have for others? And since the audience of NASEO, our members are states, what are key recommendations that you have for states that want to pursue projects and move the ball forward, including this issue of planning and coordination?
I can certainly start, Eugene. I think, from a planning and coordination, I think giving some thought to how the state might take on, the long-term nature of these storage projects, how they can clarify the ownership interests between mineral estates and surface estates, and who owns the pore space. I think those are the big sort of I would say governance types of issues that agencies really are going to have to be the leaders on, and it'll be very hard for private developers to negotiate those. So those are the big, questions I think that are going to be initially threshold for states to incentivize development, is to make those things clear. And then really understanding, what are the regulatory requirements for these types of projects, from air to waste to water, to transport, public service style, utility style requirements. One other item is, from a financial and economic standpoint, think of things that you might not always imagine in the regulatory space, but things like sales tax, income tax from a transaction of ownership of the CO2. Those items can oftentimes sneak up and really economically make or break these projects at this point.
Eugene, did you have some comments?
Rodney, I think we might have lost Eugene.
I think we lost him. Well, that's unfortunate. But we are at 3:45 Eastern, so it's unfortunate that we lost him, but it was not prematurely so, I guess. Thank you again. I will send a thanks to Eugene remotely, but thank you, Shannon, very much for a great presentation and a great session. And this has been a very rich session and series of sessions today. And I will hand it to Kelsey to offer closing remarks and close us out today.
Thanks, Rodney. So we've come to the end of day one of our workshop on carbon capture, utilization, and storage. I wanted to again thank DOE's Office of Fossil Energy and Carbon Management for their support. And also thank you to our excellent speakers and moderators for spurring such great discussion and sharing informative remarks today. There's been significant progress with decarbonization, but there's still many sectors, particularly industry, that are very carbon intensive. Innovative CCUS technologies will have a key role to play now and in the future. And as we learned today, states and state energy offices can help with advancing research, development, and deployment of CCUS and in financing projects. So tomorrow's agenda will feature a variety of CCUS policy experts, beginning with a policy outlook and then turning to an overview of the pending infrastructure bill, state perspectives on CCUS policy, and then a discussion on community engagement focused around workforce and economic development. So thank you again, and we will see you all tomorrow. Please reach out with any questions in the meantime. Have a great day.